Well, this is Electric Circuits course of second semester students in the Department of Electrical Engineering, UIT Lahore, and I'm Dr. K.M. Hassan. This is our textbook, and this is the last lecture on chapter 4. And before this lecture, I have uploaded part 1, part 2, and part 3. This is part 4. In today's lecture, we will discuss one or two examples in the operational amplifier circuit analysis and an example in operational amplifier circuit design. We will skip this for the time being, and we'll see at the end of the course, depending on the availability of time, we'll discuss section 4.6. This is an example of operational amplifier circuit analysis or active circuit analysis. Here we see that V1, this V1 and plus sign means we have a voltage source over here, V1, and other side is connected to ground. This plus sign means positive side of V1 is connected to this node. Similarly, over here, this V2 means we have a voltage source. Later we call it signal, input signal V2 and input signal V1. To make circuit simple and smarter, we don't show these, and it is enough to show positive sign over here. The positive sign, this positive sign means the positive side of voltage source V2 is connected to this node. Now let us start its analysis. In the op-amp model, we are following. We say that in the model over here, this is VO and non-inverting input and inverting input, and let us call it VP and VN. What was our assumption? VP minus VN is equal to 0. It means that VP is equal to VN. So following this assumption, here we see that V2 is connected to this side. Therefore, the voltage at this node is also V2. Then V1 is connected to the non-inverting inputs, and as the difference between these two inputs is equal to 0, we will then call it V1. This voltage is equal to V1. So this is due to the assumption in our model. And now we write equations at this node and at this node. So first of all, I will write equation at this node. So writing node equation, you know that we assume all the currents are flowing away from the node, and there are 3 branches connected to this node. Now, what is this current? This current is V2 minus V1 divided by the resistance R2. What is this current? This is V2 minus. So let us use label over here VX and label over here V5. Though the ground signal is not shown, but we will over here, we can show it the ground signal over here. So this is the ground signal. It means that this voltage V1 is positive with respect to ground. V1 and 2 both are positive with respect to ground. and Vx is positive with respect to this ground, and Vy is positive with respect to this ground. So all node voltages have a common ground reference, as we have been doing in node voltage analysis. Now, as we are writing equation, node equation at this node, which is over here. Now, the current over here, look at the circuit diagram, the current, this current is V2 minus Vx divided by R1 and plus this current, plus I entering into the inverting input of the operational amplifier. You may recall that in the model we also assume, let me leave a space over here. So in the model, what we have assumed along with this, that current entering to the non-inverting input is equal to 0, and current entering to the inverting input is also 0. Actually, these currents are so small that we can ignore these. So look at the circuit diagram. This current is over here. This is the current which is entering into the non-inverting input. And then as this current is 0, due to our assumption, rearrange this equation. This is 1 over R1 plus 1 over R2, and all the coefficients of V2 over here, and V1 minus 1 over R2 V1, and this Vx, show it on the other side, 1 over R1 Vx. So this is the equation which we have written at this node. Now we write equation at this node. So again, the current we will see, we assume, as we have done in node voltage analysis, what we do, we assume all the currents are flowing away from the node. Look at the circuit diagram, and now write equation. Writing equation at this node is what is this current over here. This current is entering into the inverting input to the operational amplifier shown at the bottom. What is this current? This is V1 minus Vx. On this side of R3 is Vx, and resistance is R3. And what is this current? This current is V1 minus V2 divided by R2 plus, and this is equal to 0. And we have written equation for the second node. Now we will, due to this assumption, this I entering into the inverting input is equal to 0, and then we rearrange this equation. This is 1 over R2 plus 1 over R3, and V1, I have considered V1, and then minus, this is minus V2 divided by R2, and Vx, show it on the other side, this is R3 Vx. Now, due to these two equations over here, we can, I think I have done some mistake over here. This is, sorry for that. This is V1 minus Vy over here, and this should be Vy over here, as I am writing equation at this node. This is Vy. So this is now okay. Now, due to these two equations, we can show that, simplify these two equations. We want to see the output voltage look at the circuit diagram. What is the output voltage? What is this output voltage over here? The output voltage is equal to Vx minus Vy. Due to the polarity of the output voltage, this is the voltage at this side, minus voltage at this side. So this is output voltage is Vx minus Vy. So I write it over here. Output voltage is Vx minus Vy. As we can find Vx from this equation and Vy from this equation, if you simplify these two equations, you will see that it is output voltage. It has again, this is the gain associated with the output voltage, and over here this is V2 minus V1. We can express the circuit in the form of a block diagram. So this is V1 into the block diagram, and this is V2, and the sign over here is a plus and this is minus. Show it over here, minus V1 plus V2, and then the gain. This is the gain. This is R1 plus R2 plus R3. Sorry, this is R3 and divide by R2, and this is our VO. This block diagram represents the circuit and the operation performed by this circuit. Now let us consider another example. This time it is a design example. This is now another example, and in this example, this is example from the textbook. We need to design a circuit to perform operation shown in this block diagram. This is again associated with the voltage V1 and over here, and this is let me verify it. This is minus, and this is VO. Means we want to implement this operation. This is 10 raised to the power 6 times V1 minus 2.6. So how to implement this operation or this equation? In implementing this, there are two possibilities discussed in the textbook. Possibility number one, option number one, is that we have an operational amplifier, and this is voltage V1 and a resistance of 10K, and from here resistance of 10 mega ohm, and then we have another operational amplifier, 1 mega ohm and 1 kilo ohm, and going to the inverting input, and our output is over here. This is VO, and here we have a resistance of 1 mega ohm and voltage. This is plus 2.6 volts. We can show a voltage source over here like this, 2.6 volts connected to ground, or we can say it is plus 2.6 volt with respect to the ground. Both are same. I will keep this. This is 2.6 volts. Now, due to the previous discussion, we can say that the voltage here, let us call it, say Vx, and just consider this part of the circuit. We see that Vx is equal to 10 mega ohm divided by 10k, and with a negative sign, and this is V1. And now consider the second operational amplifier over here. As you know, you have seen is inverting adder circuits. If this is V1 and this is V2, this is R1 and this is R2, and we have a resistance in the feedback RF. So you may recall that this is minus RF over R1 V1 and minus RF over R2 V2. Due to this, we see that over here we can write VO. We can write VO equal to minus 1 mega ohm divided by 1k multiplied by Vx, and this was missing in it, and minus 1 mega ohm divided by 1 mega ohm multiplied by 2.6 volts. And now there is Vx over here and Vx over here. Substitute this Vx over here. This is minus 1 mega ohm over 1 kilo ohm, and multiplied by minus 10 mega ohm divided by 10 kilo ohm V1, and minus 2.6, and you will find that this is 10 raised to the power 6 V1 minus 2.6, and it shows our desired results. So this is one option. Another option is discussed in the textbook, and this option is just implementing the same mathematical operation or equation with two operational amplifiers, and this time we use operational amplifier in a slightly different way. So V1, this is positive with respect to ground. This is connected to non-inverting input, and from the inverting input we have a resistance of 100 ohm, and we have a resistance of 10k, and over here, so let us call it now, let us call it Vx. And as you know, this is a non-inverting summing amplifier, and you know from my previous lectures that this is equal to 1 plus 100 kilo ohm divided by 100 ohm and multiplied by V1. I have discussed it before. I have discussed this circuit before like this. It was like this. So this is say Vi, and this was the circuit, and this was say R1 and R2, and this is VO, and VO was 1 plus R1 over R2 and Vi. So it is the same thing. 1 plus 100k divided by 100 ohm. So you can see the textbook or my previous lecture just to recall. Now Next to the circuit is there is another operational amplifier, and Vx is connected to non-inverting inputs, and from here we have 100K and 10 kilo ohm resistance, and this is a 10 mega ohm resistance, and this is a VO, and there is another 100 kilo ohm resistance connected to ground, and 2.6 volt is connected to this input, 2.6 volt. Now this is 2.6 volt and this is V1. So how to analyze this circuit? Now due to our assumption, we can say that this is also at Vx level, because Vx and this is Vx. As we have said before, Vp minus Vn is equal to 0, and V at non-inverting input is equal to V at inverting input. So this is Vx now. I'm talking about this. This is Vx. Now with this we can proceed further, and now here we have a node here, and call it Vy. This is the voltage Vy with respect to the ground. So we have written the expression for the Vx, and now we write node equation at Vy. So node equation for Vy is Vy minus 2.6 volt divided by 100K. I mean, I have considered this current, and plus Vy divided by 100K, it means I have considered this current, and then Vy minus Vo divided by 10 mega ohm, it means I have this is what is this current? What is this current? This current is Vy minus Vx, because at this end the voltage is Vx, and divide by this is 10K is equal to 0. So this is our second equation. There is another node. If you see, I will delete unnecessary things over here. There is another node. This is another node, and the voltage over here is Vx. So I write equation at this node. So if I write equation at this node, what is this current? This is Vx minus Vy divided by 10K. What is this current? This current is Vx minus Vo divided by 10 mega ohm. And what is this current? Look at the circuit diagram. What is this current? I will show it in red. What is this current? So this current is I entering into the inverting input. We will assume it 0. So due to these three equations, we can then finally conclude that VO is equal to, you have to do it by yourself. So these three equations gives us VO is equal to 0.9910 raised to the power 6 V1 minus 2.57. So this is our final expression. So compare this with the previous results. Compare these two over here. While this is perfect, which was required over here, 10 raised to the power 6 V1 minus 2.6. This is 10 raised to the power 6 minus, but this is not exactly 10 raised to the power 6. It is slightly less than 10 raised to the power 6, and instead of 2.6, this is minus 2.7. But what is the advantage with this? What is the advantage with this circuit? So we will see the advantage. So if we see the advantage of this circuit, we see that the voltage source, this is the voltage source or the signal input. It is connected to the non-inverting input, and as you know, the current over here is approximately equal to 0. So it will not load this voltage source. If we see the previous one over here, look at this circuit diagram, this V1, as this is directly connected to ground, and due to our assumption, this is almost equal to ground. So this is known as virtual ground. So the current flowing through this will be V1 over 10K. This is the current. So our circuit, this circuit will draw this much current from the signal, input signal. However, this circuit draws negligibly small current, which we can ignore. Therefore, we will prefer the second one. We will prefer this circuit. So this circuit will be preferred. Now, there is another example. This is a design example, basically. This is now design example. We need to design an interface circuit. We have a source circuit of 5 volt and resistance 50 ohm. Note that we can say that this circuit is the Thevenin equivalent of some source circuit. And now we need to design an interface. This is the interface we need to design, and in this we will see what should be in this interface. At the output, we have a resistance of 500 ohm, and let us label the currents I2 and this current I1. Our requirement is desired output power should be 200 milliwatt. Due to this information about the output power, you all know that power is equal to the product of voltage and current, as voltage is equal to IR, we can say that we can express the power as V square over R or I square R. So we know the power, we know the required power, we know the resistance, therefore we can find the voltage. So V square is the power multiplied by the resistance, and therefore V is the square root of power multiplied by resistance, and power is 200 milliwatt, and the resistance is 500 ohm, and therefore V is 10 volt. So this is VO. So this is VO. So VO, output voltage, is 10 volt. Now current. So output current from here, I will say I2 is equal to, from this, I2 is P divided by R whole square root. And this will give you 0.02 ampere or 20 milliampere. Now, first of all, we see that if we use the circuit directly to feed 50 ohm, so this is 500 ohm. So what will be the current and what will be the voltage? You can see that this will not fulfill our requirements. So I will copy the circuit over here. I will break it downwards, the circuit over here. Now we have seen that our input voltage is equal to, our source voltage is equal to 5 volt, and output voltage should be equal to 10 volt. So the voltage gain over here, we need a voltage gain of 2 is required, and we can do it quite easily. Voltage gain of 2, we can achieve the voltage gain of 2 due to the interface which is based on active circuits, mean operational amplifier, this time the operational amplifier. So we can use operational amplifier in a non-inverting mode, and say the voltage at this side plus minus, this is V1. So we apply this V1, and this is R2, and over here R1, and this is the voltage over here, this is VO, which is over here. And we see that in this circuit, V output is equal to 1 plus R1 over R2 and V1 over here. And here, if we use, say, R1 is equal to R2, say if we use both 10K, then V output will be equal to 1 plus 1 and V1, so this will be equal to 2V1 over here. So it will serve our purpose. So we can use this interface circuit, or we can use another interface circuit instead of this interface. We can use an inverting amplifier. So this is the VO, so this is R2 and R1 and connected to ground, and we use V1 over here. Now as we need a voltage gain of 2, we can say that R2, say R2 is 20 kilo ohm, therefore R1 should be equal to 10 kilo ohm, because VO is equal to minus R2 over R1 V1, so this is minus 2 V1. Note that this negative sign, you may wonder what will happen to this negative sign. This negative sign simply means that if we connect this VO to the over here, this is 500 ohm. Due to the negative polarity, this will be negative and this will be positive. As we don't bother the polarity of the voltage at the output, therefore we can use this inverting amplifier. So what is the difference between these two? The difference between these two is that in option 1, this V1 is signal voltage or input voltage is connected directly to the non-inverting input, and we have assumed that this current is negligibly small. It is so small that we can consider it 0. But here in this option, in the bottom option, as I have been saying previously, this is connected to ground. Therefore, this is also at ground level because it is not actually connected to ground. Therefore, it is called virtual ground. So it will load the source circuit. The current through will be V1 over R1. So while this circuit will not load the input voltage or the input source voltage, this circuit will not while this circuit will not load the source voltage at all, this will draw, the second option will draw some current which is due to R1. Therefore R1 should at least be 10K as a rule of thumb. It should at least be 10K. So we can use any two of these options, but due to the loading effects, we will prefer this option in the interface circuit. So there are many examples, many other examples at the end of the chapter. I will just show you just the last example in the analysis. This is apparently it is a complicated circuit for you at this stage because this is first course in electrical engineering. This is R and 2R, resistance R and resistance R. We have an operational amplifier, so inverting input, and we have resistance over here R, and we have resistance 2R. Here we have another operational amplifier. This is our output, and output is again connected back to this, and there is another input V2, and positive side of V2 is connected to this through R by 2. So this circuit has two inputs, V1, V2 and one output. So how to analyze such circuit? I will give you simply hints, few hints, and you will do it by yourself. Look, this is a node, call it A. This is another node, call it B. And this is another node, call it C. This is another node. Actually, the whole is the same node, call it D. And now write equation at node A, at node B. We cannot write equation at node C. I will explain it. And then we write equation at node D. Now, writing equation at node A. Current flowing away, current flowing away. If we write equation, this equation will be V A minus V1 divided by R. What is this current? This is current entering to the operational amplifier. Amplifier's inverting input, which is negligibly small. And plus what is this current? This is VA minus VC divided by 2R. This is equal to 0, and we can ignore this current. Now equation at node B. Writing equation at node B, we will see these currents over here. So at one by one. So add this is VB divided by R. What is this current? This is VB. What is on the other end? Look at this. Minus VO divided by 2R. What is this current? Plus I entering into the non-inverting input. And you know, due to our assumption, we will ignore this. Now, very important thing in here, consider this. See, we can say that we will say that this current is VC minus VA divided by 2R, and this current is VC minus VD divided. So what is this current? We don't know this current. Therefore, we cannot write equation at this node because we don't know the current. We don't know the current. Remember, we don't know the current. Therefore, we will skip this, and you will see that we can still analyze the circuit. Now consider VD. Writing equation at node D, this current is VD minus VC divided by R plus this current. This is VD minus VO. This is VO. Divided by R. And what is this current? This current is entering to the inverting input of the operational amplifier, and we will ignore it. And what is this current? This current is VD minus V2 divided by R divided by 2. This is equal to 0. We will ignore this current. Now I will leave the rest of it, the analysis, to you. I assume that you should be able to simplify these three equations. So from these three equations, you will see that V output is equal to, I will see V1 minus V2 or V2 minus V1. So you have to verify what is the output voltage. Let me see where I have done. So to me this is V1 minus V2. This is V1 minus V2, but you have to verify it. So we have done it with we have used two operational amplifiers in it. We have used two operational amplifiers in it. While this equation can be implemented using one operational amplifier as well. So say We have say a resistance, another resistance, and just another resistance, and this is a summing amplifier, inverting summing amplifier. And we see if we use all resistors of the same value, and here if we use minus V1 and here we use plus V1, what does it mean? It should not be difficult for you to assume that V1, this signal voltage, is connected at this input with this polarity, and this connected with this polarity over here, V2. This is V2. This is V2. So V2 positive side is connected to this, and V1 the negative side is connected to this. Now you see the output of this. So the output of this circuit is equal to VO is equal to minus this resistance divided by this resistance and this input minus V1, then plus again this resistance divided by this resistance and multiplied by V2. So I have used plus V2 over here, plus V2 over here, and minus V1 in this equation, and you will see that this is equal to V1 minus V2. And we can use two operational amplifiers, we can use one operational amplifiers, and options are many. There are many options with in the operational amplifier circuit design. So with this I will say this is the end of chapter 4, except the last section 4.6, which I have skipped. Section 4.6, I have skipped section 4.6, and I'll discuss it at the end of the course, depending on the availability of the time. My next lecture will be on chapter number 5. Thank you very much.